In the vastness of deep space, where light takes years to bridge the emptiness between stars, navigation becomes one of humanity's greatest engineering and philosophical challenges. On Earth, we have GPS, an invisible web of satellites whispering coordinates to our devices with millisecond precision. But GPS doesn't work beyond Earth orbit. Once a spacecraft ventures into interplanetary or interstellar space, it drifts into a silent ocean without landmarks, without signposts, and without a map that can be constantly updated in real time. So how do we find our way in that cosmic dark? The answer may lie in one of the universe's most extreme and reliable natural phenomena, pulsars. Pulsar Navigation Systems, or XNAV as it's often abbreviated in research papers, represent one of the most extraordinary ideas in modern astrophysics and spacecraft design, using the cosmic lighthouses of the galaxy as a natural, universal GPS. To understand why this is so powerful, we first need to understand what a pulsar actually is. A pulsar is the dense, rapidly spinning core of a massive star that exploded in a supernova. Imagine something heavier than our Sun crushed into a sphere only 20 kilometers wide, spinning dozens or even hundreds of times per second. These neutron stars have magnetic fields billions of times stronger than Earth's, and they emit beams of electromagnetic radiation from their magnetic poles. As the star rotates, those beams sweep across the sky, much like a cosmic lighthouse beam passing over a dark sea. To an observer, that beam appears as an incredibly precise, rhythmic pulse, hence the name, pulsar. Some pulsars are so regular that their rotational timing rivals or even exceeds the precision of the best atomic clocks on Earth. In fact, pulsar timing is so stable that astrophysicists can predict the arrival of individual pulses to within microseconds across years. This incredible reliability is what makes pulsars ideal candidates for navigation. They are essentially nature's own timekeepers scattered throughout the galaxy. Here's the ingenious part. By observing several pulsars simultaneously, a spacecraft can determine its position in space. Just like your phone determines its location by comparing timing signals from multiple GPS satellites. Instead of man-made satellites orbiting Earth, pulsar navigation uses celestial objects that have existed for millions of years and can't be destroyed, jammed, or turned off. This concept takes space autonomy to a new level. To make this possible, a spacecraft would need an onboard X-ray telescope or detector capable of observing pulsars that emit strong signals in the X-ray band. X-rays are chosen because they're less affected by interference and because X-ray pulsars tend to have sharply defined pulse patterns. The spacecraft measures the arrival times of pulses from several known pulsars, compares them to the expected arrival times based on known pulsar ephemerides, essentially their timing models, and calculates its position relative to those sources. It's triangulation on a galactic scale. In 2017, NASA's NICER instrument aboard the International Space Station conducted the first successful demonstration of this idea. The experiment, called SEXTANT, short for Station Explorer for X-ray Timing and Navigation Technology, used observations of pulsars to autonomously determine the station's orbital position with an accuracy of about 10 kilometers. That might not sound impressive at first glance, but consider this. It was the first time in history a vehicle determined its position using sources beyond the solar system. It was like watching a ship navigate the ocean for the first time using stars instead of coastal landmarks. Since that milestone, the technology has rapidly advanced. Researchers have been refining pulsar timing models, building smaller and more efficient X-ray detectors, and testing the computational algorithms needed for real-time navigation. The ultimate goal is to create a self-contained navigation system that allows a spacecraft to traverse the solar system, and eventually interstellar space, without constant communication with Earth. Deep space missions today rely on the Deep Space Network, a global array of massive antennas that track spacecraft signals. It's incredibly effective, but it also means every navigation update depends on communication delays that grow as distance increases. A signal from Mars takes minutes to reach Earth, from Pluto it takes hours, and from another star system it would take years. Pulsar navigation eliminates that dependency entirely. Imagine a future spacecraft on its way to the outer planets, a robotic probe exploring the icy moons of Jupiter or Saturn. With pulsar navigation, that spacecraft can know exactly where it is, in real time, without waiting for instructions or confirmation from mission control. Or imagine a crewed mission to Mars, operating autonomously even when Earth is on the far side of the Sun. The crew would no longer rely on Earth-based navigation corrections, they would have their own cosmic compass. The mathematics behind pulsar navigation are both elegant and complex. Each pulsar has a well-documented timing signature, a pattern of pulse arrival intervals that can be predicted using relativistic models accounting for spin-down rates, gravitational influences, and even glitches in the neutron star's crust. By comparing the observed pulse phase to its predicted phase, a spacecraft can determine its range relative to that pulsar along the line of sight. When it does this with multiple pulsars, each defines a sort of hyperbolic surface of possible positions, and the intersection of these surfaces gives the precise spatial coordinates of the observer. The accuracy improves as more pulsars are observed simultaneously, much like how your phone's GPS becomes more accurate when more satellites are visible. One of the key challenges lies in building detectors sensitive enough to capture pulsar X-ray signals while remaining small and energy efficient. Early pulsar detectors were large observatory-scale instruments, but modern microchannel plate detectors and silicon drift sensors are dramatically shrinking that footprint. Some research concepts suggest that a functional pulsar navigation array could fit into a device no larger than a suitcase, powered by the spacecraft's onboard systems. Beyond spacecraft navigation, the implications of pulsar-based timing ripple across multiple scientific fields. The same technologies could enhance our understanding of gravitational waves, test Einstein's general relativity under extreme conditions, and refine the galactic coordinate system itself. Pulsar navigation is not only about knowing where we are, it's about defining space and time in an absolute, universal context. Pulsar navigation systems could eventually extend even beyond our solar system. For example, a future interstellar probe sent toward Alpha Centauri could carry a pulsar-based guidance system that constantly updates its position against the known pulsar map of the Milky Way. Even in the emptiness between stars, it would never truly be lost. And that's where the philosophical weight of this technology begins to shine. Humans have always looked to the heavens for navigation. Ancient sailors used constellations to cross oceans. Explorers used the North Star to find their way. Pulsars are the next generation of that cosmic map, stretching the concept of wayfinding from oceans and planets to the very fabric of the galaxy. Of course, there are challenges to overcome before pulsar navigation becomes standard on spacecraft. Pulsar signals are incredibly faint compared to typical cosmic sources, and timing stability can be affected by phenomena like pulsar glitches, sudden changes in rotational speed caused by internal starquakes. Moreover, to maintain long-term accuracy, spacecraft will need updated pulsar timing models periodically. That means pulsar navigation will likely operate in tandem with traditional radio tracking for some time. Still, the trend is clear. Autonomy is the future of exploration. As human and robotic missions push farther out, communication delay and control latency become major limiting factors. A spacecraft capable of determining its own trajectory, adjusting its course, and maintaining synchronization with universal time will fundamentally change the scale of missions we can attempt. Imagine autonomous mining fleets operating in the asteroid belt, each using pulsar signals to navigate. Or fleets of robotic explorers dispatched to the outer solar system, coordinating among themselves using pulsar time references rather than Earth's network. Pulsar navigation could even be the backbone of future interplanetary internet systems, where spacecraft synchronize through galactic timing rather than local networks. In military and defense applications, the idea of navigation independent of Earth-based infrastructure is also compelling. Pulsar-based systems cannot be jammed or spoofed like GPS, making them ideal for strategic spacecraft or deep space assets. Even scientific observatories could use pulsar timing to maintain orientation and calibration across millions of kilometers. In essence, pulsar navigation systems represent the next evolutionary leap in how humanity interacts with the cosmos. They merge the ancient art of celestial navigation with cutting-edge astrophysics and quantum-level timing precision. They transform stars from distant observers into active participants in our journey outward. The deeper you think about it, the more profound it becomes. The same stellar remnants born from catastrophic supernovae, objects once considered symbols of death, could guide the future of life across the universe. Every pulse, every beam of radiation sweeping silently across space, carries within it the potential to orient travelers who will one day cross the interstellar void. Pulsars are cosmic lighthouses, yes, but they're also anchors in space-time, constant points in a changing universe. When we finally send probes beyond the heliopause, or crewed missions to other star systems, those explorers will navigate not by human satellites or terrestrial commands, but by the rhythm of the galaxy itself. Their coordinates will be defined not by longitude and latitude, but by the pulse beats of ancient neutron stars, spinning endlessly in the dark. And perhaps, centuries from now, when humanity spreads into multiple star systems, we'll still measure our distances not in kilometers or miles, but in pulsar coordinates, a galactic standard rooted in physics, not politics. Just as GPS reshaped global civilization, pulsar navigation could unify interstellar civilization. The first time a spacecraft located itself using pulsars, humanity proved something remarkable. That even in the vast, indifferent emptiness of space, the universe had already provided us with a map. The stars themselves have always been the compass. We just had to learn how to read their language. Pulsar navigation systems are not just about getting from point A to point B. They're about transforming the way we define where we are in the cosmos. They are the next step in the ancient human tradition of exploration, bridging the wisdom of ancient starlight with the ambitions of a species destined to travel among it. And that, perhaps, is the greatest lesson of all. Every beat of a pulsar is a cosmic heartbeat, echoing through time, guiding not only our ships, but our destiny, to the stars. Hey everyone! If you enjoyed this video, make sure to hit that like button, drop a comment to share your thoughts, and subscribe so you don't miss any of our future uploads. Your support helps this channel grow. Thank you for watching.